This lecture is part of a series of lectures on rings and modules and will be about formal power series rings. So the first example we will look at is the collection of formal power series over the complex numbers, which is normally written like polynomial rings, except you put two square brackets in there. And a typical element of this ring is just a formal power series a0 plus a1x plus a2x squared and so on, where the ai are in the complex numbers. And the point is you don't worry about convergence. So for example, 1 plus 1 factorial x plus 2 factorial x squared plus 3 factorial x cubed and so on is a perfectly good formal power series, although it doesn't actually converge for any non-zero value of x. Back in the 19th century, people used to get really nervous about formal power series and thought they really ought to converge, otherwise they don't make sense, because if it doesn't converge anywhere, then it's not a function. And how do you define multiplication and so on if it's not a function? Well, that's quite easy, because a formal power series is really just a sequence of elements a0, a1, a2 and so on. And addition and multiplication of these sequences is defined by pretending that they are formal power series. So the formal power series is just to tell you how to multiply two sequences. I mean, you could define the product of two sequences without writing them as formal power series, but it would be rather incomprehensible. You would say that this sequence times the sequence b0, b1, b2 and so on is equal to the sequence a0, b0, a0, b1 plus a1, b0 and so on. And this is really rather unintuitive, so it's much better just to write them as formal power series. The idea of a formal power series ring is it's, on the one hand, they're rather like polynomials, because a power series is really just a polynomial except you forgot to stop. And on the other hand, they turn out to be a bit like real numbers, because they have a sort of completion property, and it's easy to take limits of formal power series, whereas in general you can't take limits of polynomials very easily. So there's an alternative, more algebraic way of constructing formal power series. Here I'm going to work over any ring R and look at the ring of formal power series over R. And this is going to be defined as the inverse limit of the rings of the polynomial ring modulo the ideal x to the n. So I will now explain what this means. So what this means is we take all these polynomial rings divided by x to the n. So the first one will be r of x modulo x, which is rather a silly way of defining the ring R. And we can think of elements of this as being just elements a0 of R, or more precisely we should say a0 plus some unknown multiple of x. If we look at r of x modulo x squared, then that means we're ignoring x squared and above, so elements of this ring can all be represented as a0 plus a1x plus something times x squared. Let's write O of x squared plus O of x. And r of x over x cubed is similar. Its elements look like a0 plus a1x plus a2x squared plus some multiple of x cubed that we don't really care about. And now what does the inverse limit mean? Well, the inverse limit means you pick elements of all these rings here that are compatible. Well, what do I mean by compatible? Well, compatible means that they must be compatible with the natural homomorphisms between these rings. So you might think we've got a natural homomorphism from this to this by taking a0 to a0 plus a1x, but we don't really, because it's not really a0, it's a0 plus an unknown multiple of x, and we don't know what to take it to. However, we do have homomorphisms going back in the other direction, because if you know something modulo x cubed, you certainly know it modulo x squared. So an element of the inverse limit means we take a constant plus a linear term, a constant plus a linear term plus a quadratic term, and these all have to be compatible, which means the constant terms must be the same and these terms must be the same and so on. And obviously that's the same as just taking a formal power series. So the formal power series ring can just be defined as the limit of a polynomial ring with respect to an ideal. Actually, you can do this more generally for arbitrary rings. If we take any ring A, commutative ring A, and an ideal I, then we can form the inverse limit of the ring A modulo I to the n. So when A is equal to the ring of polynomials and I is the multiples of x, then this just gives the formal power series ring. And this is called the completion of A, and sometimes denoted by A hat. And complete rings behave very much like formal power series rings in many ways. There's one particularly famous example of a complete ring, which is the p-adic integers, denoted by z sub p. By the way, algebraic topologists have this habit of using z sub p to mean the integers modulo p, z modulo pz. And the trouble is this notation is ambiguous, so really it's much better to use z modulo the z times p to mean the integers mod p, since this is ambiguous. This is unambiguous, whereas you don't quite know whether this means the p-adic integers or the integers mod p. Anyway, the p-adic integers is just the completion of the ring where you take a to be the integers and I to be the multiples of p. So we just copy the construction of the formal power series ring. We take z modulo p squared, z modulo p cubed, and so on, and there are natural maps between them, and we just take the compatible elements of each of these. So an element of z mod p, well, let's write it as a number, except we're going to write it as a number in base p. So a naught is equal to 0, 1, 2 up to p minus 1. And an element of z modulo p squared we can write as a base p number as a1, a0, where a1 is again one of these numbers. So we think of this as being an integer written in base p, except we only bother with the two lowest terms of it. And z modulo p cubed, we're going to get a2, a1, a0 dot something. And if we extend this, we find we get an integer written in base p, except it's not an integer because it goes off infinitely far to the left. And if you think about it a bit, you'll realise that you can actually add and multiply things like this just using the usual rules of arithmetic, and everything kind of makes sense. So it's a bit like real numbers. So a real number like 3.14159 and so on, it goes off infinitely far to the right, but you can still multiply things together. And instead you can let things go off infinitely far to the left and everything still works, and that gives you p-adic numbers. You might wonder what happens if you let it go off infinitely far to the left and infinitely far to the right, and that doesn't work, because then if you try and multiply things together you find you get lots of meaningless infinite sums. This is actually pretty similar to formal power series, because you remember this expression essentially just means a0 plus a1p plus a2p squared and so on. So it almost looks like a power series in p, except it's not quite, because when you add things together you get carries. I mean, if you add, say, if you add two numbers together, you might get a carry and find that a1 suddenly becomes non-zero and so on. So p-adic numbers are similar to formal power series, but they're slightly more complicated. Let's have a look at what the structure of the formal power series ring is. First of all, let's look at the ideals of the ring of formal power series. I'm going to work over a field to make things simpler. And first of all, we notice there's only one maximal ideal. So this already makes them a lot simpler than polynomial rings. And the reason for this is that if a0 plus a1x plus a2x squared and so on is a formal power series, and a naught is not 0, this has an inverse. And that's quite easy to see. We can multiply by a0 to the minus 1 because k is a field. So we may as well assume it's of the form 1 plus b1x plus b2x squared and so on. And let's write this as 1 plus x times g of x. And then it has an inverse, 1 minus x times g of x plus x squared g of x squared plus x minus x cubed g of x cubed and so on. We can just formally write down the inverse, and you notice that this is a perfectly good power series because the increasing powers of x here make sure that this sum is actually well defined. And since everything with a non-zero constant term has an inverse, so can't be in a maximal ideal, we see the only maximal ideal is the ideal of multiples of x, just the power series with zero constant term. Well, it's not much more difficult to find all ideals of the ring. You can easily check that all ideals are just given by either the ideal 0 or they're generated by powers of x. So it's particularly easy to factorize elements. The only irreducible element is x, and every formal power series is some power of x times a unit in a unique way and so on. So it's got unique factorization and everything is really easy. In particular, it's a principal ideal domain. Now let's have a look at formal power series and two variables. Well, here this is not a principal ideal domain because it has non-principal ideals generated by, say, x and y, all power series with zero constant term. And in fact, the ideals of this get quite complicated. Well, you may remember that the ring of polynomials in two variables is Noetherian. And we proved that by showing that if R is any ring, then R is Noetherian, implies the ring of polynomials is also Noetherian. And by iterating this, we see that the ring of polynomials in any number of variables over a field is Noetherian. Now we're going to do the same thing for power series rings. What we want to do is to show that R being Noetherian implies R, that the ring of power series in X is Noetherian. So let me just reuse these words Noetherian to save ink. And the idea is to copy the proof for polynomials, except the proof for polynomials doesn't quite work. So for polynomials, you remember what we did was we wrote down these ideals In, which is generated by the highest degree terms of polynomials a0 plus an x to the n in I. So In is going to be generated by the numbers an. Well, this fails for power series rings because power series rings don't have a highest non-zero term, so we can't do this. So we don't quite copy the proof for polynomials. What we do is we take the proof for polynomials and instead we modify it as follows. We're going to let In be the ideal generated by the numbers an, where an x to the n plus an plus 1 x to the n plus 1 and so on is now in I. So here we're taking all powers of x less than x to the n to be 0, whereas for polynomials we're taking all coefficients of x to something for something greater than n to be 0. So it's like the proof for polynomials, except we're somehow turning things upside down. We're looking at lowest coefficients rather than leading coefficients. So anyway, now we have ideals I0, I1, I2 and so on if we're given an ideal I. So I should have said let I be an ideal of Rx. And we get a sequence of, these are ideals of the ring R, and it's easier to check. We get an increasing chain of ideals because you can just multiply by x to go from I0 to I1 and so on. And now we can complete the proof more or less as for polynomials. And I'm going to leave that as an exercise because it's really quite similar to the proof for polynomials. I should say there's one slight extra catch you have to worry about. So let's leave this as a question. Why does this proof not work for polynomials. So if you try to prove that R Noetherian implies Rx Noetherian for polynomials and try to use the lowest degree terms like here, you'll find that the proof doesn't actually work. There's a special property of power series you need to use in order to complete this proof here. So for proving Noetherianness of polynomial rings, you have to use the highest coefficients, and for power series rings, you need to use lowest coefficients. We also showed that if R is a unique factorization domain, this implies R of X is a unique factorization domain. And this implies if you've got the ring of polynomials over a field in several variables, this is a unique factorization domain. And what we want to do now is to show that the ring of formal power series in several variables, let's just do 2 variables, is a unique factorization domain. And there's an obvious way to attempt this. All we have to do is to show that if R is a unique factorization domain, then R of X in the ring of formal power series is a unique factorization domain. And we're not going to prove it this way, and the reason we're not going to prove it this way is very simple. This statement here is actually false. There are examples of unique factorization domains such that the ring of formal power series over them is not. If you want to see an example, there's an example given in Samuel's book on unique factorization rings. So we need to use an extra idea in order to show that the ring of formal power series in several variables is a unique factorization domain. And what we're going to do is we're going to use the Weierstrass preparation theorem. And the Weierstrass preparation theorem, let me say what it looks like formally first. It says that a power series in several variables, k, x, y, z, and so on, can be made to look like a polynomial in x. So we can you can think of this as being something like a sort of change of coordinates or something. So here we've got a function which looks rather complicated, but by changing coordinates and massaging the function a bit, we can sort of make it look like a polynomial, not in all coordinates, we can't do that, but we can at least make it look like a polynomial in one of the coordinates. And this will be enough to push through the proof of unique factorization. Well, now I'd better state more precisely what I want to do. What I'm going to do is I'm going to prove the Weierstrass preparation theorem for polynomials in 2 variables. The proof for n variables is kind of similar, but notation becomes rather a mess. So the key idea appears for 2 variables. So if we're given f as a polynomial in 2 variables, what we can do is we can write f is equal to a unit times a special polynomial in x, as a n minus 1 x to the n minus 1 and so on, plus a0, where these are power series in y, and I guess we also need an extra power of y, which I always forget whenever I discuss this theorem. And the unit is harmless. And I guess I should have said f is not 0. If your power series f is 0, then there's obviously not much difficulty in dealing with it, so you don't need the Weierstrass preparation theorem. And this bit here is called a Weierstrass polynomial. So you see it looks like a polynomial in x, but it doesn't look like a polynomial in y. We've still got this infinite power series in y, but that's sort of good enough. And the idea of the proof is, well, what this is saying is that a lot of the coefficients of f kind of vanish if you multiply it by a suitable unit. So the idea of the proof is to kill off coefficients of f by multiplying f by suitable units. And the units we're going to use are just units of the form 1 plus something times a power of x times a power of y. And these are all going to be units because their constant term is 1. So in order to see how to do that, let's draw a picture of f. So we've got a power series here, and what we're going to do is we're going to have monomials. I'm going to put y on the x-axis and x on the y-axis for no particularly good reason. Just used to thinking of it this way. So we have all these, so we draw a point for each monomial, and we can then think of a power series as assigning a coefficient to each of these points here. And the Weierstrass polynomial has the following coefficients. First of all, it's got a coefficient of x to the n. So let's just put n equals 3 here. So this coefficient can be non-zero. And then it's got a lot of coefficients that are polynomials in x times something in y. So these coefficients can also be non-zero. And in fact, we can do a little bit extra here because these can be power series in y with 0 constant term. So in fact, I can arrange for these coefficients here to be 0. So all the other coefficients are going to be 0. So the coefficients down here are going to be 0. And all these coefficients up here are going to be 0. So that's what we've got to do to f. We've initially got a polynomial with lots of non-zero coefficients everywhere, and we want to kill off all the coefficients in blue. And what we do is we start off by looking at the coefficients up here, and we want at least one of these coefficients to be non-zero. So we multiply by some power of y, so that coefficient of some power of x is not 0. So this is where this easily forgettable power of y comes in. We need to start by sort of shifting f so that something in this top left bit is 0. And then we're going to pick n to be the smallest power of x whose coefficient is non-zero. So these coefficients here are all going to be 0 by the choice of n, and this coefficient here is going to be non-zero, and we can find at least one non-zero coefficient because we're assuming that f was not identically 0. So far we've managed to get this bit right. And now we've got to somehow kill off all these polynomials in blue. So let's see how to do that. And what we're going to do is we're going to kill off all these polynomials in a very particular, we're going to kill off all these coefficients in a very particular order. We're first going to kill this one, then that one, and then we're going to kill off this entire row. And then we're going to come down here and we're going to kill off all the things that are y times the power of x. And then we're going to come down here and kill off all the things that are y squared times the power of x. So we're sort of zigzagging up and down and killing off the coefficients one by one. And now let's see how to kill the coefficients. So suppose we've got these coefficients 1, y squared and so on, x squared, x cubed say, and we've got a non-zero coefficient here, and we've got various non-zero coefficients here. But suppose we've managed to kill off some of the coefficients. So we found these are 0, and we've managed to make all these ones 0, and maybe, you know, we've managed to make all these coefficients here 0. And we need to work on this coefficient here. So let me put it in a big box. We want to kill this. We want to kill off this coefficient. And it's going to be something times x to the n plus I times y to the j. for some I and j, where I and j are greater than or equal to 0, and at least one of them is positive. And we can kill this coefficient. How do we kill this coefficient? What we do is we multiply f by 1 plus something times x to the I times y to the j. And we carefully choose this something so that the coefficient of x cubed will kill off the coefficient here. So if we multiply this by x to the I, y to the j, we're mapping x to the n to x to the n plus I times y to the j. So we can kill off one coefficient by multiplying by this unit here. And we notice this is a unit because its leading coefficient is 1. Constant coefficient is 1. Now the only thing we have to check is that we now have some sort of infinite product of things of the form 1 plus something times x to the something times y to the something. And all we have to do is to check that this converges as a formal power series, and that's not very difficult to check because there are only a finite number of terms where the degree of this bit is less than some constant. So if we multiply all these infinite polynomials together, we still get a well-defined formal power series. So that proves the Weierstrass theorem for polynomials in 2 variables, and as I said, the n-dimensional case is kind of similar, although as you can imagine, the bookkeeping gets somewhat messier. Now let's go back and use this to prove that the ring of polynomials in several variables is a unique factorization domain, except, as I said, I'm just going to do the 2 variable case because this gives the essential idea. Well, there's an easy part. Every polynomial, sorry, every power series is a product of irreducibles. And this follows because the ring is Noetherian. And the proof of that is the same as the proof I gave or possibly didn't give earlier for the case of polynomials, so I'm going to skip it. Then there's the hard part where we need to show that f irreducible implies f is prime. And you remember f irreducible means f can't be written as g times h for unless g or h are units, and f prime means that if f divides g times h, then f divides g or f divides h. So irreducible implies prime is the key step of showing that anything has unique factorization. So what we're going to do is suppose that f divides g times h, and now we can assume that f, g, and h are Weierstrass polynomials by the Weierstrass preparation theorem, because the Weierstrass preparation says we can arrange this by multiplying everything by units, which obviously makes no difference whatsoever to anything, and we can also may need to multiply by powers of y, and that's also obviously totally harmless. So f, g, and h are Weierstrass polynomials. So we have f times r is equal to g times h for some power series r. Now the key point is that r is a Weierstrass polynomial. And in order to do this, I'm going to use something that I didn't actually prove about Weierstrass polynomials. This follows from the fact that Weierstrass polynomials are unique. This is something else you should really check, but I'm going to leave this as an exercise. If we replace r by its Weierstrass polynomial, then f times r is still a Weierstrass polynomial, and it must be the Weierstrass polynomial of g times h because Weierstrass polynomial is unique. And that means that r must already have been a Weierstrass polynomial to start with. So the fact that r is a Weierstrass polynomial follows from uniqueness of Weierstrass polynomials of formal power series. Well, now it's easier to finish because we know FR is equal to GH, and we now work in the ring of formal power polynomials whose coefficients are polynomials in X, and we notice that all of these now contain F, R, G and H, and we notice that F is irreducible in K, Y of X, because if it was reducible as a polynomial, it would certainly be reducible as a formal power series. So this implies F is prime in this ring here, because this ring here is a unique factorization domain. Well, why is it a unique factorization domain? Well, it's a polynomial ring over a unique factorization domain, and we know this is a unique factorization domain. If we were doing several variables, we would have to be using induction, but for one variable, this is obvious. So this implies that F divides G or H in this polynomial ring. So it must divide G or H in the formal power series ring, which is the same as K with formal power series in both X and Y. So this proves the key step of unique factorization, that primes, so that irreducibles are prime, and therefore the formal power series ring in any number of variables is a unique factorization domain. So I'll just finish by giving some traps you can fall into. You have to be a little bit careful about the difference between being divisible in a polynomial ring and in a formal power series ring. First of all, if F divides G, G in a power series ring K, X, Y, this does not imply that F divides G in the ring where we just use polynomials in X. So although F divides G in this ring implies it does in that ring, the converse doesn't hold, and that's very easy to see. For instance, we might have G equals 1, F equals 1 plus X, and these are both units in the power series ring, but obviously F doesn't divide G in the polynomial ring. Another example is that if F is irreducible in the polynomial ring, it need not be irreducible in the power series ring. And a typical example of this is F is equal to y squared minus x cubed. If you've done algebraic geometry, you may remember this as the equation of some sort of cubic curve. It's not quite an elliptic curve because it's got a singularity, and this curve doesn't break into two components. It's an irreducible curve, and this is just an irreducible polynomial. However, in a formal power series ring, well, you can notice that this is saying y squared equals x squared times 1 plus x. And now in a formal power series ring, we can just take the square root of 1 plus x. So this is x times we can write this as y squared minus x times the square root of 1 plus x, all squared, is equal to y plus x times the square root of 1 plus x times times y minus x times the square root of 1 plus x. So we've managed to factorize this in the formal power series ring. So what's going on geometrically is the formal power series doesn't see this whole curve because it only converges in an infinitesimally small neighbourhood of 0. I mean, it really only converges at 0, but let's pretend it converges in an infinitesimally small neighbourhood. So you can think of it as it kind of sees an infinitesimally small bit of that curve and an infinitesimally small bit of that curve. So the formal power series ring thinks that this curve actually splits into two curves. You're sort of magnifying it near the origin, and it kind of looks like that. So these two formal power series correspond to the fact that this curve seems to have two branches near the origin, although if you go further away from the origin, you can see that they aren't really two branches at all. So another thing you must be careful is do not confuse the polynomial ring k of y with coefficients in x with the ring polynomials in y followed by power series in x. So this is formal power series in x whose coefficients are polynomials in y, and this is polynomials in x whose coefficients are formal power series in y. And these kind of sound the same, but for example 1 plus xy plus x squared y squared plus and so on is in one of these rings but not the other. So it's in this ring but it's not in this ring because it's not a polynomial in x, but all its coefficients are polynomials in y. Another similar example is that if you take rings of Laurent series, so if you try inverting x and y, so you can invert x and invert y, then you can also first of all invert x, and then you can take power series in that and then invert y, or you can do it in the other order. And these three rings are all totally different. And it's easy to get totally confused between them. You may think these are all just the ring of Laurent power series in two variables, but the trouble is there are several completely different rings of Laurent power series in two variables. For example, these two rings both contain an inverse of x minus y, but the inverse of x minus y is different in these two rings. And one of them it's 1 over x plus y over x squared and so on, and the other one it looks completely different. It's minus 1 over y minus x over y squared and so on. So you have to be rather careful if you're trying to invert x and y in formal power series rings, because there are lots of different ways of doing it. Incidentally, you can't form a ring take formal power series in both directions. This ring either doesn't exist or collapses down to 0 or something. If you try and form this, you just run into contradictions. Okay, so the next thing I want to discuss is Hensel's lemma for formal power series rings and related rings like the p-adic numbers, but I will postpone that to the next lecture.